Hello everyone. This lecture is on mass spectrometry. Mass spectrometry is a technique which is a detection technique for various molecules, and is this technique is part of many equipments when the molecules are separated and they they are unknown or even they are known, just to identify their quantity as well as if they are unknown, just to know which molecule is present in the mixture. This is a very important technique which is uh, used to identify molecules. So we'll talk about the principles and some of the applications as you can see. As we know, different elements can be uniquely identified by their mass, and we know that from the periodic table, all these elements are arranged according to their mass. Mass of an atom is basically because of their uh, protons and neutrons present in the nucleus. So that's where the mass of the atoms or those elements they come from, and the hydrogen, lithium, so all they are all arranged by going from mass 1 to mass 2, mass 3, mass 4. So mass is organized, and that's how these all these elements are organized. So all these molecules, various examples are there of these uh, ethanol to dopamine and other molecules. They are when you count the number of carbons, oxygens, hydrogens, nitrogens, and calculate and add their mass together, gives you the mass of the molecule. And mass actually is unique for that particular molecule. So if there is a mass of 46 in a mixture of compounds, it's most probably is because of ethanol. Ethanol is not the only molecule with the 46 molecular weight, but still, most probably, if you know the type of mixture you're dealing with, you will see this mass spec. Um, so this method is just to understand the basic is to measure the molecular or atomic weight of the sample. So adding all the molecular um, all the atoms, the weight of the atoms together gives you the molecular weight of the molecule. So that's the basis of mass spectrometry, and that molecular weight is unique for that particular kind of molecule. Okay, so for small molecules, this technique is very accurate. It can determine the molecular weight within 5 ppm error. Uh, so it's pretty accurate. And for large molecule like molecular weight for proteins, the accuracy is around 0.01%. Uh, Not bad, but still for 50 kilodals. Kilodals, if you remember, is the delta. One dalton is one atomic mass, so 50 kilodal, 5 dal difference can be there. So that is pretty accurate for most part for the measurement of the molecular weight. So the principles. So now, how do we determine the molecular weight of a compound? So first, we need to charge the equipment. The method requires a charge on the molecule. A positive charge most of the time is required. So then this charge, when it is placed in the magnetic field, it and it is flying through magnetic field. I'll show you some pictures later, but it's flying through the magnetic field. It forms a curved path, and the curved path, the radius of the curve is related to mass to charge ratio of the molecule. So I'll show you later how what I mean to say with that. So just understand that there is a charge which is moving through a magnetic field, and when it is moving, it follows a curved special angle depending upon the mass to charge ratio. Since the charge is normally 1, so it depends on the mass of the molecule. And then there is a photo multiplier detection tube which can detect the ions, and depending upon where on the plate it strikes, you can actually calibrate that how much the molecular weight that could be. um, so sample, it it is charged, passing through an ionizer, and ionizer means it's ionizing. Ionizing means it is separating positive from negative charge, electrons from the molecules, and giving a positive charge to the molecule most of the time. And then there is an equipment in which this moves, and then depending upon the mass to charge ratio or mass of the molecule, various ions move in this different directions, and they strike on the plate at different places. And if it strikes here, we know the molecular weight is low maybe, and if it strikes on this side, molecular weight is higher. So that's how we know how much the molecular weight is. And there is a spectrum which gives you lines, and those lines indicate what is the molecular weight of particular uh, mixture or that passing it through. I wanted to watch a couple of videos to see how, just some some information will be repeated, and but you can visually see what is happening in these videos out there. So continuing with that, so for how the ionizers work is that they are high energy electrons, and they break the molecule into fragments. So it is not one fragment or one molecule with a charge. When the a high energy electron strikes a molecule, the molecule fragments into different pieces, and we will see later on that how what I mean. But it breaks down into say 2 pieces or 5 pieces depending upon the size of the molecule and where the weak bonds are. It breaks it down, and then those fragments are flying. They are charged. They are flying through the magnetic field, and they depending upon their molecular weight, uh, they will strike, and you can see which fragments are present at the end of the mass, and then you can combine them together to make the total molecule. So that's okay. This is an image of a schematic of mass spectrometry um instrument, how it is laid out. So you can see that the sample is entered or subjected into the machine by a probe. These are the black are the sample molecules. Electron beam is produced high energy electrons, and they produce ions here when they strike with this. So black ones are sample molecules, and then when they strike with electrons, they produce a regular stream of ions which are produced. So when these ions are accelerated into a tube, they pass through a magnetic field, and now you can see one beam, and small and big dots are present. They separate into 3 streams: very small molecules as far as mass is concerned, middle is the medium size molecules, and bigger ones are the big size molecules. So they follow a different path when we pass them through the magnetic field, and depending upon now the slit where the um molecules are, or these ions are passing through, the detector can detect and can give you a chart that where these molecules are, which line they are following, which angle they are following. So if they are following bigger angle, bigger angle is probably this one, then it is smaller molecule, lower angle is for the larger molecule. So you can detect the various parts of the various fragments from there, and some of these molecules will be original molecule which entered here and just had a charge, so it will be the largest molecule in the mixture of the fragments. Okay, so let's continue. So as we discussed that charge is important, the charge on the molecule is important and that will cause the different curvature when they pass through the magnetic field. Radicals are not charged; they are neutral molecules, so they will not form a curvature path. They are invisible to mass. So radicals are out of the question. So they are not going to be detected by the mass spectrometry. Amount of deflection is observed depends on the mass to charge ratio. As I told you before, most cations formed have a charge of 1. So I discussed that or told you these things before, but they are here written form. So the amount of deflection observed is usually depend on the mass of the ion. Charge is usually 1, so you can cancel it out for all the molecules. So it is directly proportional to the mass. Here is an example now. So you have a methane gas, and in the high energy electron, they produce a cation with methane molecule, but just they picked up one electron out of this two electrons in CH bond. Only one electron is left, and the rest is positive charge due to an extra proton inside the carbon. So this is methyl cation. So that has one positive charge. The molecular weight or MZ ratio, M over Z ratio is 16, which is the molecular weight of methane. If you get a peak for 16, then most probably it is methane. So this is how we detect these molecules. So the graph which you saw before or will see later on also is the graph of each cation versus its relative abundance. Abundance means how much quantity. It means the quantity of that cation. The peaks are assigned as abundance as percentage of base peak, the most intense peak in the spectrum. So most of the peaks, so one peak you will see as the highest peak. That is called as base peak. And all the spectrum is organized as percentage of base peak. So the highest peak is considered as 100%, and the rest will be organized, or it is calibrated according to that 100%. It's like percentile we calculate when we take exams. The highest score is 100 percentile. So this is also organized. These graphs are organized in that same way. So base peak is remember two terms: base peak and parent peak. Parent peak is the biggest molecular weight in the spectrum. Most probably it is the molecular weight of the whole molecule. Many times molecules the intact molecule without fragment being fragmented also forms a parent ion, and it may not form the parent ion all the time, but many times it has a parent ion, which is the whole molecule together, and it has a charge, and um, that can be there can be a peak related to that, but it may not be the highest intensity peak. So high intensity peak may be something which broke out from the parent ion, and it forms the highest intensity peak. So base peak and parent peak can be different. So in this case, for ethanol, the molecular weight is 46, as we discussed before. 46 is related to methanol or ethanol, sorry, and the the this peak is 46. It's a parent ion peak or parent peak, but the base peak is this one. So base peak can be different from the parent peak. Base peak is the highest intensity peak. All these peaks are going to be given as percentage of this peak, the base peak. However, this peak, if present, it gives you directly the molecular weight of the molecule. You can think of that I am running a solution or something I got from somebody, and they say I don't know what is in this mixture. Can you detect it? And I run it through mass spec, and I got a peak of 46. I can say this is ethanol. So somebody brings you an ethanol bottle and they don't have a label on it. you can run it through mass spec. If there are peaks, these peaks present, you can quite definitely say it is ethanol. So it's kind of an important detection technique. uh, Many times it's combined with the NMR, some other techniques, but also it can be individually used for that part. So this indicates you base technique, base peak, and this is the parent ion peak. Um, Another thing to keep in mind is many times many of the elements, they have a isotope. Like in carbon 12 is the main atom, but carbon 13 is also present in rocks. Carbon dating, how they calculate how old certain rocks are, how old certain fossils are, they do by isotope deterioration or degradation methods. So isotopes are present, and they can give you double peaks, which are corresponding to the isotopes of the particular element. So, like bromine has two isotopes. So, if two isotopes at that molecular weight, those two peaks are present, it means bromine is present. So, it is kind of an identifier for those elements present in the molecule. Um, Okay, and also one other thing to keep in mind is nitrogen has odd molecular weight. If you have an odd molecular weight ion, most of the time nitrogen is present. So these are just some people have found over the time. As I told you before, bromine has two isotopes which are very close in concentration. Um, the molecular weight of 79 is 50% and 81 is 49%. So if there are two peaks related to the 50-50 concentration, they are equal amount present in there, then bromine is present. So this doublet indicates bromine. Just additional some of the techniques. Similarly, chlorine has one isotope which is one third of the molecular with one mass. So if you have 1 to 3 ratio of these two peaks, then most probably chlorine is present in the molecule. So it indicates, you cannot guarantee, but you can just say that yeah, it is. If it is 4%, then sulfur is present. So there are two peaks always present at the ratio of 4% to 96% of it is present. Similarly, iodine has molecular weight of 127. So if you see the molecular weight has certain iodine peak, you can detect the iodine in the sample. It's a large molecular weight, so you can see the parent ion and the next ion can have a large difference in the um, in the spectrum. So these are tricks and tips which have been used to identify easily certain special ions present in the whole mixture. Um, so so the bottom line is that the impact of the stream of high energy electron often breaks the molecule into fragments, commonly cations and radicals, and those uh, they get stable cation and also radicals, but radicals are not very important because they are not detected by the mass spec. So that is the what we see in there. So now this example will clarify some of the concepts which we have discussed so far. So you have ethane molecule, electron strikes, but electron can strike anywhere. All these CH bonds are kind of equivalent for this electron. So it can extract electron from this side. It can this can further lose hydrogen radical and form a cation like this, or this can also strike or break down from here to give you cation radical of this. Radicals are not going to be detected, whereas cations are going to be detected. So if the molecular weight is 30 for ethane, you may get a peak for 29, you may get a peak for 15. So this is a simple example, but if you go to complicated molecules, there can be complicated fragments. These are fragments of the parent molecule. So this is the parent ion. These are fragments from the parent molecule. So you can see this once you are expert in these techniques, looking at them again and again, then you can easily see that, oh, 30, there is 29, there is 15. So anything containing 15, you will know it is a methyl group or methyl cation. So that's how uh, are the molecules. So parents, in case of so these are parent ions for methyl and ethyl. So parent ions are radical cations corresponding to the mass of the original molecule. And molecular ion is usually the highest mass. So these are molecular ions present in there, and mostly that is the peak which you see, the highest peak you see. And but sometimes the molecular ion peaks are absent. They are not present all the time because they may not survive. They may break. All of the molecules, they break to smaller fragments, so you may not see the molecular ion. So now, just going back, if you see a 15, it's a methyl group. 29, ethyl group. Propyl is 43, butyl is 57. So if you see these numbers on the molecular weight mass spec, then you can identify these peaks by these fragments or these molecules. Branched alkanes tend to fragment, forming a more stable carbon. So to survive and transport through the magnetic field, they need to be enough stable so they don't break. So carbocations should be stable while they're passing. These are just some of the example. I'm going to skip also, and this is just to show you that how it looks like when you see the spectrum. Again, give you just one of the example. This is allylic carbocation. So one principle you can remember is whenever there is a charge or a radical character in a molecule, it is more stable when that radical character or cationic character is dispersed over various carbons. For example, in this case, if a carbocation is present at this carbon, due to the resonance structure, this can move from here to here due to the resonance. So now this positive charge is located over 3 carbons. It's more stable than if it is just staying on one carbon. So that is a general rule of thumb, that you are dispersing the energy over a bigger area. So this is more stable cation. Anyway, so you can calculate the molecular weight of this, but this is a molecular ion. Again, this is the base peak, which is the highest. This is the parent ion peak, and rest of the peaks correspond to certain fragments, maybe methyl, maybe ethyl. So if you find a peak in there, this corresponding to 26 or 29 or 15, they are corresponding to certain fragments from this molecule. That's how we determine all this. So similarly, if benzene is present, there are certain peaks which are going to be present in the spectrum. So this corresponds to tropylium ion, which is the base peak here in this case, whereas the molecular ion peak is here because bromine is present. So there are two isotopes, although they are very small, but it indicates that bromine is present, and this is the molecular weight of this benzene benzylic ion containing bromine. Another example showing you that odd molecular weight with nitrogen present, and this is the base peak after NO2 is gone. So the benzene gives you always 77 peak. For most of the aromatic compounds, they give you 77 peak. Okay, finally, that you can separate various molecules. We'll talk about GC also next time, and I will also talk about this in the lab. So when the molecules separate from these column chromatographies, it can pass through mass, and we can detect which kind of molecules are coming out. Each fragment, each fraction when passing through can be detected by mass. So it's not just one molecule. If you have a mixture of 10 compounds, they can be separated first by GC or HPLC, and then each of those 10 can be passed through mass spectrometry, and we can detect each one of them separately. So it is combined with a separation technique also. Summary of the lecture is that mass spectrometry is a tool for checking the molecular weight of unknown compounds. It is a sensitive technique and provide a lot of information. It's expensive machine, yes it is, and you need a technically trained person to run this machine. And mostly LC, GC, I will show you this in the lab. They are used to because you want to purify by using LC and GC, and then mass spec is used to detect them. So you separate and then you detect them, because mixture in itself we cannot detect. So you have to separate them first, and then you can use mass spec to detect the components. Okay, so far this is the and I will continue further in the lecture part again with HPLC and GC. Okay, see you guys soon then. Thank you. Bye.